And week 10, EE546, recurrent neural networks. And regarding the lectures, this is the week before the last one. So we've got 2 more lectures, including today. And today we are going to talk about a journey, actually, because I'm going to still be introducing you some concepts, which is from encoder decoders to transformers. And actually, this is a very nice discussion. I'm sure you're going to like it. So, before we begin, what we've done so far, we've done a lot of things. So, what we've done so far, slides, is becoming very crowded. It's okay. From understanding what a sequence to very complex architectures, which are hybrid in the sense that they both process signals like vision signals or text. That's the journey. And at some point, we've concluded a part of the journey with CNN plus RNN architectures. And the previous week, we started talking about natural language processing because natural language processing was deeply affected by the use of LSTMs especially. And for the previous years, LSTMs have seen a wide usage in this field with word2vec, because word2vec in 2012, it provided us with the ability to convert a language. It could be English language or C++ syntax, whatever, to numbers. And when it's numbers, LSTMs work. That was a revolution in the field. And actually, following that revolution, newer developments have arrived. Actually, I'm going to be talking about one of the important ones, transformers, today. But before I begin, I'll have to make this, guys. I've said this multiple times in the previous video. I'm going to say this again. Neural NLP, including word2vec, including encoder-decoder architectures we have introduced the previous week, which we are going to continue today, including the concept of attention, recurrent model of attention, which I'm going to introduce you today. The following concept of transformers and the concept of attention, which will be different than the recurrent model of attention, of transformers, and actually all parts of transformers, positional encoding, multi-headed attention, whatever we are going to cover today, partially. These are all very intense subjects, guys. It is impossible to fit them in 2 weeks. Next week, I'm going to be talking about them a bit more with some new subjects, but they need a course of their own. So consider this as an introduction to the field. With this introduction, I think you'll be ready to use them in proper context. So that's a start. However, getting deeper into the architectures of these models, the current model of attention or transformers, which we are going to see today, is a different story. You'll need a lot of time, but however, if you plan to do this in your research, in your master's or PhD study, I think this is a nice starting point. That's why I've chosen to place them and just give a place to them in my course. Okay, guys. So we were talking about, encoder-decoder architectures, remember? Actually, what we've introduced the previous week was, instead of using a single LSTM, we said that maybe using 2 different models, the first one of which encodes the input, and the following one, the second one, decoding the input, seemed like a better idea. Why? Because when you are doing especially this problem, sequence to sequence problem, so you are given a sequence, you're providing a sequence, and you are just expecting a sequence. The nature of the input sequence and output sequence are likely to be different. So instead of just one LSTM handling the properties of the input and the output to be generated, 2 separate inputs just connected to each other, one responsible for encoding the input to a higher level representation, like meaning. Remember, we were talking about meaning the previous week, just like philosophers do. Then the second part, getting that meaning, that high level meaning, and converting it to the output. And the first ever encoder-decoder idea of recurrent models is actually new. I mean, there always have been an idea of encoder-decoders, but first proper usage of encoder-decoders was by Cho et al. Cho et al. Said that, well, let's not use LSTM single. Let's use an encoder LSTM and a decoder LSTM. Encoder LSTM, or whatever recurrent neural network, they didn't say specifically LSTM, it could be a GRU, or a more complex recurrent model. Any model that is capable of working with sequences. And any model that is capable of providing sequences, encoder and decoder. They provided this idea. Actually, it was, in a way, revolutionary as well. It's one of the most cited papers now. And it was Joshua Bengro's team. And Joshua Bengro will be a part of this NLP, neural NLP a lot. We're going to see his name in a lot of papers, guys. They proposed the very first RNN-based encoder-decoder that consists of two recurrent neural networks. One recurrent neural network encoding a sequence of symbols and creating a fixed length vector representation, which you may say the concept. And the other one getting the concept and turning into another sequence representation. This could be German to Turkish translation, or this could be a chatbot asking a question, getting the answer, both the question and the answer being sequences. So kind of the neural NLP journey of and their relation engagement with recurrent neural networks kind of had a boost with this paper. Following that paper, guys, there was another paper, which was much more important. They said that, okay, this is a very good idea. We could have an encoder, we could have a decoder. And the encoder transforms the encoded text to a meaning. And the decoder gets that text out. Very good idea. But there's a problem with this. Because what we are trying to do, if it is a translator, for example, let's go over the translator example. I am the translator, okay? I am simultaneously translating somebody speaking, okay? You've seen this in football matches, which is terrible, by the way, but a better example of these cases is political translations. I mean, very important political meetings like Davos. You have these guys, they are certified guys. They don't do a single mistake, because if they do a single mistake, you could start the world war, so they don't. So what, if you ever come across these guys working, they take notes, guys. They take notes, because sometimes the guy speaking in one language constructs very long sentences. And you know the problem with very long sentences for recurrent neural networks. A very long sentence means very long dependencies in our sequence, which is fairly difficult to learn. Okay, we've got LSTMs, we've got many mechanisms to get over it. So we don't have vanilla RNN now. We can learn many things, larger sentences. Okay, instead of 4 word sentences, we now can translate 7 20-word sentences. However, sometimes it's very long. So while you're doing that, those guys take notes, because the guy says something very important about the sentence. For example, the guy is translating something about a meeting between two countries, and he says about the third point of that, about the contract's third bullet, it would say. At that point, the guy takes a note so that it doesn't say the fourth bullet or whatever, another part of the contract. We call this actually attention in a sentence. I'm going to be using this word a lot today, attention. This is what it's all about. Some parts of the translation is more important than the other parts. So if the translator could take notes, that would have been a better translation. That's how we do, how simultaneous translators do. And actually, their idea was to operationalize this idea in encoders and decoders. So what they've got was, actually they worked on translation. It was in the paper English to French translation. They have introduced the idea of attention as a mechanism between, wait for it, I'm creating an attention now, wait for it, between the hidden states of the encoder to the hidden states of the decoder. So at each point, the encoder creates hidden points, right? At each new word coming, it creates some hidden, not hidden points, hidden states, if I say hidden states. Those hidden states are lost. The last representation is the total representation of the sentence in a regular encoder-decoder architecture. However, if we could just keep some of the hidden states and provided that information to the decoder's hidden states, because decoder's hidden states are renewed as new words come. If we could take a similarity between decoder's hidden states and the encoder's hidden states, well, that would be like finding what is related to what between the translation and the translated, and that could create an idea of attention, they say. Okay, I'm going to go into very deep into this mechanism. I'm just trying to introduce you the idea first. So the first successful application of E to the idea was in language translation was Sutskever paper, because they had attention. They've used a multi-layered LSTM and encode both to encode and decode the text. It was an English to French translation. Okay. So this is how the great journey of neural NLP started with EDs, guys. Was this the attention paper? Yes. No. Sorry. Yes, it was the attention paper. So before getting the attention, I've got some slides I remember now. I'm going to introduce you some other concepts about the encoder-decoder networks. So in this encoder-decoder architecture, you had this, in the middle you have the representation. One of the important problems was the cost-loss function. So before I get to the attention, I'm going to introduce you the idea of the loss function in a translation. What is the output? It is a sentence. How do we calculate the loss of a sentence while we are training it? I love artificial intelligence, or I love intelligence artificial. So the first one is correct, the second one is wrong. But how much wrong? Shall I give the same penalty to I love intelligence artificial sentence or a crappy sentence which I could not translate? So they should have different kinds of losses. To calculate the amount of loss is very important, and it's very difficult, because in images, when you're trying to just calculate the category, we had softmax. When you're trying to calculate some value, you have norms like L2 norm, L1 norm. In regression, we have mathematical tools to calculate that distance. However, in language processing, this loss concept is a bit difficult. There are in the literature different ways to calculate this loss. In this NLP literature, one of the most common loss functions are the bleu and rouge. They are actually French, because mostly the authors were French and they used the abbreviations which corresponded to color names in French, which is bleu and rouge. They have different strategies. The two very famous ones, the most two famous ones are bleu and rouge. The bleu is a kind of loss function, which we are not going to get into detail, measures the precision. So how many words exists in the translated one. The other one is the recall. So it is like bleu is how much words in the machine generated summaries appeared in the reference summary. So how many words it checks the bleu, yeah, kind of. The rouge, the other one checks how many words appeared. They are the same sentence. What was it? Arkadaşlar yazarken yanlış yazmışım. Hatırlamaya çalışıyorum bleu ve rouge'dan hangisiydi. I'm sorry, I remember. Bleu is how many same words existed. Rouge is about, rouge is about how many same words existed. Okay, so you have a bunch of words. And in the translation, you have a bunch of words. The similarity of the words. Bleu is how many words existed in the right places. So it's about the precision, the place of it. So they are both important, because if you use a wrong word to translate something, it's a wrong translation. So, for example, in Turkish, I'm saying çok iyi bir insansın. If I say you're a very proficient person, Well, that's wrong. You're a good person, I should have said. Well, that's the right word usage, which is related to rouge. And another one is çok iyi bir insansın. Very good person you are, if I say, just like the same order in Turkish. That's another mistake. And Bleu takes care of this, guys. Okay, good. So when you're dealing with NLP, you'll have to use these loss functions. And actually, most of the papers in neural-based natural language processing, they try different loss functions because one loss function can take care of another property while the other one can take care of another property. So when they train their system, they present their results with different loss functions to show in which way their results are good or bad. Good. So before we get into the details of attention, we now know what is the loss function for NLP. So if any of you try to just, I don't know, train a system, they know the loss functions now. A text-based system. For example, if you are translating a coding language, precision is much more important because the recall won't be a problem because you'll have a smaller vocabulary. So that's why you just choose the proper loss function for the proper application. Okay, I'll get back to NLPs. So let's just calculate it somehow. We just go there. And there are very nice studies. Actually, in Hacettepe University, there are Erkut and Aykut Erdem brothers, twin brothers, maybe you've heard of them. They've studied this a lot. They've studied different loss functions for image captioning, and they've come up with their own strategy and loss criteria as well. And so I recommend you read their papers. They've been working on this specific stuff, the loss of natural language processing, for a long time. Okay, this kind of approach, having an encoder and decoder, sorry for the voice, allows the input and output sequence have a great flexibility. But I said there's a problem. When the input gets very long and long and long, maybe the meaning, the conceptualization, that fixed length representation that we have at the middle will have more information from when we just look at the input sequence, would carry more information from the, last parts of the input compared to the initial parts of the input, because the input is very long. As if the translator was listening to the guy and he forgot what was the first sentences or the first words of the sentence were. So as if it is the case. So we'll try to make that guy take notes. And we are going to call that mechanism recurrent model of attention, guys. So before we get to the recurrent model of attention, these are some factors that I just mentioned about the problem of not having attention. So actually, I guess this was the attention paper, right? Not Sutskever paper. This was the attention paper, I guess. I may confuse them. Just check it, okay? The potential issue of this decoder-encoder approach is that neural network needs to be able to compress all necessary information of a source sentence to a fixed length vector. This will make it difficult for a neural network to cope with long sentences, just like we said, especially those that are longer than the sentences in the training corpus. So in this training corpus, you've got some bunch of sentences, you've got a distribution of the length of the sentences. So the translator gets a longer sentence and it breaks off. We need a category, we need a mechanism for that. So actually, Cho et al. Showed this in the very first paper that provided the idea of encoder-decoder. They were aware of this problem. This was a problem that they could not solve. So encoder-decoder is good, but when the length of the sentence get longer and longer, we have a problem. Actually, this figure is from their paper. So this is the sentence length, and this is the loss function, the Bleu score. As the sentence lengths get longer and longer, their Bleu score, success, Bleu score is a bit not like loss, guys, it's the score. So to get the loss, maybe you just get the negative of the Bleu score, whatever, mathematically. This was a problem they had. Even if they used LSTMs, they couldn't get over this problem. Because although LSTM can get longer dependencies, it has a tendency to remember the latest comer, which is the last part of the sequence, compared to the previous comers. So if the input sentence is too long with respect to the fixed dimension, then we cannot avoid the loss of some information from the initial parts of the sequence, and the translation will be affected from it. Okay. Just like we said, just like I introduced, a solution to this problem was so-called the attention mechanism. At this point, I'm going to make a warning to you. There will be two types of attention, guys. The attention that I'm going to introduce you now will be the recurrent model of attention, which will relate the hidden states of the encoder to the hidden states of the decoder. However, attention in general can be used for different mechanisms, which calculates similarities between sequences. So now I am going to introduce you the recurrent model of attention, which was introduced by the Bada newspaper, not Sutskever, I guess. I'm going to get there and show it to you, don't worry. Okay, so what is it? During the encoding phase, at each step of the RNN, we can store the hidden state. Okay? Then during the decoding step of the second RNN, let it be an LSTM, not just a vanilla RNN, never. We also keep the hidden states and we construct the next example, not using only this hidden state, but also using some weighted or operationalized averaged version of the hidden state of the encoder as well. So it is like using our notes while we were listening to the guy. Because never forget, for a translator, listening is the action of the encoder. Translating is the action of the decoder. So the notes that we take, we were listening as the simultaneous translator, is the hidden states that we save in this attention mechanism. Okay. The weights of this average depend directly on the previous decoder's hidden state. So the weights of the average will affect, actually, not depend directly to the previous decoders. So this will, in this case, so how are we going to do it? I'm going to get into the mathematics of it, don't worry. So the idea is, while we are doing this, the hidden states of the decoder will be created by the recorded hidden states of the encoder. And this is called attention, guys. This is called the attention mechanism. Okay, so I think you have a general idea of what attention, recurrent model of attention is. Now I'm going to get deeper into it. Then I'm going to just define it as a layer to you, and we are going to go over each step of the layer. Okay? At any time, if you have any questions, please stop me. Okay. As a very brief summary, at each step of the decoder, we are going to highlight information from a small subset. I've got a GIF, so let me just wait. I'm going to do something nice, and I'm going to connect to my computer because we need those guys. Let me get there. I'm keeping you waiting. Sorry. Okay, so guys, it is as if you can see the animation now, right? Can you? Anyways, yes. Can you can see?
Yes. Yes, you can see.
Okay, sorry. So it is. We have the encoder. There is a sentence. As the encoder comes, I'm saving the hidden states, which are H1 to 4. And I'm using some sort of average of these, not, I say weighted average because they are the weights and that's the part you learn. Actually, it could be a weighted average, it could be another mechanism. Not getting into the details now. There are different implementations of attention, don't worry. By using a function of these attention, I'm creating the next function, I'm feeding it to it. So I'm combining the hidden states of the decoder with this information as well. So I'm combining the hidden states of the decoder with the previous information. Okay, so this is the generic scheme of the decoding phase of an encoder-decoder architecture which has the recurrent model of attention. I think you have a very simple idea of what's going on. So the key fact of attention mechanism is you need the context vector. What is the context vector? When you combine the weighted average, somehow weighted average of the hidden states, and this guy that we obtained, the decoder's hidden state, we combine them. We take a similarity of the decoder's hidden state to the previous hidden states. And actually, we will call it the context vector. That context vector will shape the next hidden state of the decoder, and it will help the translation. So how exactly the context state is generated and how it is just helping the decoder states generate the output, I'm going to get into those details. I'm trying to introduce you that, the context vector. The context vector is a mathematical output of a function which takes the hidden states of the encoder and the current state of the decoder. Any questions? Okay. So, öksürüğüm gitsin diye içiyorum. Daha fazla öksürüyorum. Pardon, şey. So, this way, actually, this context vector said it's an output of a function which uses the encoder's hidden states and the current the hidden state of the decoder. Actually, it calculates a distance from the decoder's hidden state to the weighted average of the encoder's hidden states. We are going to get there. So how it's going to make sense. So at this point, I have so many questions in my head. How are the weights learned? How exactly we feed the loss to this layer? So if it's going to be the hidden states, how I'm going to just train it? How am I going to test it? What is the mechanism? There are so many questions. I will be able to answer only some of them. But in the end, with these answers, you are going to understand the mechanism, and you are going to also understand that there are multiple combinations of this mechanism which it can be created. So there are multiple ways that you can create this mechanism. Let's get there. So this attention, yes, Badanu's paper, I'm sorry, Suskever. So Cho's paper was first encoder-decoder architecture. Suskever's paper was first encoder-decoder architecture applied to machine translation, language translation, without recurrent model of attention. And Badanu's paper, the same year, was the first encoder-decoder architecture with the recurrent model of attention. At that point, attention never lost its importance, guys. Attention is one of the most important concepts in NLP now, even today, this very day moment. Okay, so it was again Joshua Benju, guys. He's the guy. So if I don't remember his name. Evet, Toronto Üniversitesi'ndeki Godfather of şeyin adı neydi arkadaşlar? Beyin durdu. Neyse işte, if he is the godfather of CNN, I think Joshua Bengio is the godfather of neural deep learning, whatever. So in this paper, they introduced this recurrent model of attention with an encoder-decoder model. Actually, this paper led the foundations of the very most important paper of NLP today, which is Attention is All You Need by Vaswani today. It is the paper transformers are introduced. A transform is a concept which we are going to today. It is one of the steps that created that paper as well, because this paper introduced the idea of attention, and that paper has taken that one step further. So it is about that history. So attention is an interface connecting the encoder and decoder that provides the decoder with information from the encoder's hidden states. With this framework, the model is able to selectively focus on valuable parts of the input sentence and hence learn the associations between them. And when you learn the associations between them, you make a better translation. You know what is important in the input sequence and what is not important, so you do your translation accordingly. And is this mechanism a separate layer? Yes, it is a separate layer. So I'm going to introduce you the basics of this separate layer, guys. So let's just try to focus on this layer. So This is the encoder. It's a single LSTM, for example. And these are the, this is the single LSTM, Arnoldine type. So it is not, you don't have multiple LSTMs. Never just think of that in this course at least. So this is the first word, this is the second word, which is the vector representation of the third word, fourth word. And at each state, you are creating a hidden state. I mean, you are feeding it to the next state as well. But imagine we are outputting, we are saving it. Okay. And the output of the decoder will be fed to the decoder as well. So to create this layer in between, it is like this. So just think of this as being connected, guys. Okay. This is a continuation from here to decoder, and this is the decoder. Okay. The first decoder time step, we are getting ready to receive the information from the encoder before giving the first translated word. So before getting the output, we are feeding the inputs and saving the encoder states. Attention is the interface between encoder and decoder. It's like a layer. It will provide the decoder with information from every encoder hidden state. Good. With this setting, model will be able to selectively focus on the useful parts of the input sequence and hence learn the alignment between the sentence, because that alignment is actually what makes that language mean something, guys. I mean, there's a difference between, you can change the words, but sometimes in many languages, the way you construct the sentence may help the meaning and may help construct the meaning. Okay, this is another discussion about transforms. We are going to get there. But by the way, guys, there's a nice GIF figures here, animated figures here. I've taken them from this guy's website. So just visit it, this blog, on this blog. Definitely visit it. He makes longer explanations. I'm going to introduce and just summarize it. Definitely go there. And the links are also in the final pages of your PDF. Okay. We could, in very general, categorize any type of attention into two categories: the global attention and the local attention. Because at this point I said, I'm using all the hidden states of the encoder to create the next state of the decoder. If you use all the hidden states of all the encoder inputs, because in encoder, maybe the input sentence was 8 words, maybe it was 12 words. In that case, you'll have hidden states, different states, same as the number of words, right? If you use all of them, it's called global attention. You are trying to understand the distance of each word translated to the input sequence words. Or you could use a global attention, local attention, in which this number is limited. So it is like, for the first sentence, only the first 4 sentences will be related. Is this a good idea? It could be, or it could not be. When you're translating a language to another, for example, Turkish to English, that's definitely a bad idea, because most of the sentences we construct in Turkish are reversed in order when you construct them in English. So that's definitely a bad idea. However, if you are translating from C to Java, that could be a good idea. And making it small actually will make your system train better. So just remember that the attention, the relation between the hidden states and the next hidden state could be for all input or not the whole input. Because when you're just, imagine you're translating from Java to C, you'll be translating line by line, instruction by instruction. In that case, it would be maybe local, could work. I've never tried it myself, but logic says so. Okay. So this paper is also another paper which introduces global attention versus local attention. It's also another important paper, 2015. And it is led by Manning. You remember Manning? The previous week's CS 224 lectures in Stanford. You remember? So it's Stanford neural NLP professor. Oh, it was their paper, and it's a very important paper as well, because if you care to use some local versus global attention, and if you have some discussions, you'll definitely cite this paper. Okay, so we continue to understand recurrent model of attention plus the history. So guys, at this step, we prepare the available encoder hidden states, okay? So hidden state, the green, and the first decoder hidden state. So we have saved them. So we just saved them, we fed it, and the first decoder hidden state is constructed. Okay. We have 4 encoder hidden states in this simple example. That means we have, if we are using global attention, which means the input sentence is 4 words. It was something like intelligence, I don't remember. Translated from something. Note that the last consolidated encoder hidden state is fed as input to the first time step of the encoder. So this is fed here as well. So it's created. So using these hidden states, I am going to be feeding the hidden state information to the next decoder time step. But not only it, I'm going to, in this layer, I'm going to combine these whatever hidden states, green hidden states, with this hidden states and combine it that way. How? At any point, please stop. So I'm going to combine these and fed it. How? At the second step, we obtain a scalar score function. This is the way it was first proposed in Badanu's paper, guys, which we call the alignment function. Alignment, what is it? I'm going to get to what alignment is in a couple of seconds. The score function in this example, there are different ways to calculate it. This is called the alignment function. It could be of any function, but in this example, let's say that how I calculate this. I get the dot product of this guy with this guy and calculate the score. It could be a dot product, or it could be something else like adding or cosine similarity. I'm trying to calculate actually a similarity between this one and this one, this one and this one, this one and this one, and create a score out of it. Remember, dot product is actually like a similarity of 2 vectors in an orthogonal space. You are mostly electronic students, so you know what I say when an orthogonal space from linear systems theory. So what I'm trying to say is, when you get the dot product of 2 vectors, actually you are calculating something like similarity. Any questions at this point? Any questions at this point? I thought I heard some mics. Okay, don't worry. So I said just a second about alignment. Sorry. Just get back. Get again. We said alignment. What I'm trying to do is, for each hidden state, I'll be creating a word. I'm trying to get the similarity of each word to each guy of the input. So actually that alignment vector is my similarity, my relation to that word. So in this example, if this score is higher, or if this score is higher, this one is higher, I think that the first sentence is more related to this word of the input, because that's a similarity. Well, you may ask, well, how it's working this way? Well, actually, we'll be training the system to make it that way. When you have this mechanism, the weights of the encoder and decoder LSTM will be trained accordingly. So you are creating this mechanism so that the outputs of these LSTMs are shaped accordingly. So it's like, how can I put it? Preemptive mechanism that will help the training. Okay, so that's the alignment. Alignment means matching segments of the original text with their corresponding segments in the translation. So the figure in the middle shows that this, if this was a sentence, la is related to d. So that score of that value is to be higher in this mechanism that we desire. If it is, because if we can make the mechanism work, then it will make sense. So you can ask just the same, I'm asking the same question. How come the hidden states will be such that their dot product will give high value? Well, we're trying to make that work like that. We're pushing this mechanism so that the hidden states will be such with those trained weights. Good. So it's okay. If you see there are other lines here, so the purple, white, so depending on the darkness of the line, the strength is higher. So La is very strongly related to do, but it's also related to European and economic as well. It's not related to agreement, for example, in this, because it doesn't have significant values. Good. You got the idea. Now I've calculated the alignment score. Good. At this state, what is the alignment? So imagine the decoder hidden state is this, and the hidden states of the inputs are these guys. You'll have these scores if I'm using the dot product, the inner product. Any questions about this mathematical example? Well, I assume that this second one is higher score, so it should be more related to it. Okay, the next step. I'm going to be...
Hocam pardon, bir şey sorabilir miyim?
Hı hı.
Mesela skorlardan 2 tanesi eşit olursa o zaman ne yapıyoruz?
Well, actually, it could be the case. Then I would think that we are not doing anything actually. We are trying to understand the mechanism, Sanem. So I'm going to translate your question such that what does it mean when the weights are similar? So would that question satisfy you?
Yes.
Okay, I can answer that question. It would mean that in that language, translated language, that word is equally related to both of these words. So it was like a very stupid answer, but that's the only answer I can give, because we cannot put forward in very clear words what is the relation between two languages. But we know that in languages, some words are related to the translated words more compared to some other words. So it is like a measure of alignment, similarity, relation, correlation. I'd say that those two have both similar correlation to that word. We can think of something like that. Because, for example, we could find a very nice example. Sometimes in one language, one word can only be represented by two words. So in that case, that would be the case. Isn't that so? Think of something like that. Can anybody give such an example? In one,
You mean like a synonym?
a synonym, but in one language, it is one word. In the other language, it is represented by two words, a two-word phrase. So I can think of I cannot think of something like that. Böyle olunca düşünemiyorum.
Şey olabilir hocam, siyah ve kara olabilir.
But they are synonyms. In my example, in one language, the other one has two words. So you need two words to represent it. I'm trying to think of an example. Think of a two-word phrase in Turkish, for example. What's a two-word phrase? So, very good example, very good example. So, çok üzüldüm. Çok üzüldüm. I'm using two words. I'm using çok to just intensely express my sadness, right? I can say I'm very sad. In this example, very will be related to çok. Sad will be related to üzüldüm, right? Think of a word in English which would mean you are very sad, but you don't use the word very. Can you find it? I couldn't find it. I am devastated. So devastated will be equally related to çok and üzüldüm, kind of. So that's a good example.
Tamam hocam, anladım.
Okay, so sorry. Slaytlarda kendi kendine heyecanlı slaytlar. Okay, so in this example it was that. The next thing we do is we apply a softmax function because we want normalized results. So you know what a softmax is. We just covered it in the previous semester's course, which was softmax is you take the exponentials and normalize it by the sum of the exponentials. And actually, when you apply softmax, I have applied it in MATLAB, you got these values. So if you have 50, 60, 50, and 35, these are the results of the softmax. So in this line, they are kind of truncated because it's like zero. Even this one is like zero. Okay? So this one will be zero and this one will be 1. Okay? So at this point, I have a distribution of that relation which is normalized. Because in the end, I'd expect that in the translated sentence, a word's relation to all the words in the sentence summing up to 1, right? It could be just, in the like this example, it could be just complete relation to a single word or something else. Just the one that we've talked about, çok üzüldüm, devastated kind of 0505, whatever. Okay, the next step. So I've got some explanations, let me read them. We take the, okay, so I've done those explanations. Then we multiply each output of the softmax score with, then we multiply each encoder hidden state by its softmax score. So this one with 0, this one with 0, this one with 0, this one with 1. Guys, this will be, in this case, the only one related to it. This is exactly the mechanism the alignment is taking place. Because in the next phase, I'm going to sum them up. So the traces of these will be lost, right? And I will have the context vector. The context vector represents the relation of the current hidden state of the decoder to all hidden states of this guy. So it will be a linear combination of these guys. It could be an addition, or it could be some kind of weighted addition where the weights could be learned. A different version of that alignment calculation. That's not an important detail, guys. We are trying to understand the mechanism right here, the recurrent model of attention. Okay. So a context vector is an aggregated information of the alignment vectors from the previous step. Okay, I've got the value. Finally, we feed the context vector to the decoder. How it is done? There are different ways to do it. I mean, there are some common ways that people always do, but doesn't matter. Can we feed, should feed as an input or as a hidden state, weighted hidden state? So I've got a context vector. I've got the next decoder hidden state. So how am I going to feed it? As the self state or weighted version? Doesn't matter. That's a practice. There are different just practices, not getting into the details. Somehow you are feeding it to that LSTM. And that LSTM, somehow trained that way, learns how to use it, makes the translation accordingly, guys. This is called the recurrent model of attention. Before we give a break, I have provided the example for language translation. But actually, it doesn't have to be language translation, because it could be anything. If you're feeding the input and you're getting the output of a dynamic system, for example, a control system, or plant. You are trying to simulate a plant or a controller. Given an input, what the output should be. So you're given an error, and you're given the current state of the motor or the device, and you just want this output. The current is the output. I'm sorry. The error is and the state is the input. The current to be provided to the servo motor. Well, that's a dynamic system. Well, in those cases, and attention is also important because there are a lot of detail coming in. And if you knew which part of the previous information is important, for example, there was something very important. You've seen something important in the input, a trace of some hard friction, then your model should behave accordingly. Actually, attention-based control systems are very, very, novel concepts that people are just working on these days. So it doesn't have to be only translation. It could be a control system as well, because this is an LSTM versus LSTM encoder decoder. When you add the attention, you have more capability of this system to get information from the input and provide it to the output, and to know which part of the input is more important for the generated output of the decoder. Okay, I'm going to go over this slide again, and I'm going to finalize our discussion. The basic model has no weights, so no training, but you can change. Can it have weights? Yeah, when you calculate the alignment vector or context, you can change this. How to learn if it has weights? It could be backpropagation. So why weights? Well, maybe to make local operations. Maybe you're trying to use local attention and you want to focus on the neighborhoods. I don't know. It could be anything. So the training is, since this is a computational graph, is backpropagation. Okay. Any questions before we give a break?